Okay, guys, I'll begin. Hello, everyone. Welcome to Lecture 4 of the Mechanical Design course. This lecture is over mechanical components. Finally, it's not physics. The last two lectures have been long-winded lectures about math and science and all of that stuff. That's boring. We're going over the cool stuff now. So what will we cover this lecture? We're going to go over gears and gear ratios, chains and belts, bearings and linear slides, linkages and springs, and actuators. So first, let's start with gears and gear ratios. What is a gear? Gears are spinning discs that use teeth in order to transfer power between one another. They are mostly used for two primary purposes: changing direction of rotation or creating a gear ratio. What are gear ratios? A gear ratio is the ratio between the number of teeth between two interacting gears. These can be used to change the speed and the torque being outputted. This works by using mechanical advantage, where distance and force, torque in this case, are inversely proportional. So what I mean by this is that when you have a smaller gear rotating and it goes a full 360 degrees, it would rotate a bigger gear by less than 360 degrees. So it has less distance. And if we were here for physics, you have work. So less distance, but you have the same amount of work means that they have more force, so torque in this case. So that's mechanical advantage. So here's a gear ratio example. The red gear has 14 teeth and the green gear has 42 teeth. So in this case, the gear ratio is 42 to 14 or 3 to 1 when simplified. That means that the output of the green gear will have 3 times the torque, but will have 1/3 the speed, vice versa. So if the red gear was the input gear and it was spinning and it's spinning 360 degrees, it would spin the green gear by 1/3 of 360, which would be 120 degrees. So the green gear will be spinning at 1/3 the rate, so 1/3 the speed, but in exchange, it'll have 3 times the torque. So it'll be able to output 3 times the amount of force per the distance away from the axle. So here's a gear ratio problem. We need to cause the output to have 5 times the torque. Assuming the input gear has 12 teeth, how many teeth will the output gear have? So the correct answer here is that the gear ratio have to be 5 to 1. And since we want to increase the torque, we need to make the output gear have 5 times the teeth. Therefore, it will have 60 teeth. Here's the second problem. We need to cause the output to have 2 times the speed. Assuming the input gear has 20 teeth, how many teeth will the output gear have? The gear ratio will have to be 2 to 1, and since we want to increase the speed, we need to make the output gear have 1/2 of the teeth. Therefore, it will have 10 teeth. Velocity and torque ratios. We don't just have to use the teeth to figure out the gear ratio. If we take the velocity of the input gear and divide it by the velocity of the output gear, we can get the inverse of the gear ratio. So in this case, a 1 to 2 velocity ratio is equivalent to 2 to 1 gear ratio. We can do the same with torque, but instead of it being the inverse, it'll just be directly equivalent to the gear ratio. So instead of using number of teeth, you can just use the difference in velocities or the difference in torque. So why should we use gear ratios? Most of the time, the torque and speed combination we get from an actuator is not ideal for our robot. We use gear ratios to manipulate those two variables to be the most efficient at doing the job at hand. So most of the time, especially with motors, as we'll go over later, are really, really, really fast and have really, really low torque. So we want to gear up in order to make sure that the actual torque and speed is good for purposes of our robot. Here's some examples. A heavy lift typically needs torque more than speed. So we typically use very large gear ratios. So in this case, about greater than 21. I would say, especially for certain motors, we would probably be looking at closer to 50 to 1 or 100 to 1 gear ratios for a heavy lift. An intake likely requires more speed. So we use smaller gear ratios. So in this case, 2 to 1. So once again, motors go really, 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 really fast. So we almost never try to gear for speed after a motor. But in this case, we just gear a little bit for torque. So we have a small gear ratio of 2 to 1. A drivetrain needs a good balance between torque and speed. So in this case, I said around 7 to 1, which is the average gear ratio for swerve drive modules, which is what we use on our robot. Any questions?
Will you cover like how planetary gears work or no?
Yes, we'll go over the types of gears just next.
All right. Thank you.
Okay, let's move on. Back to gears. So here's the different types of gears. There are many different types of gears, all with different purposes. So we have spur gears, helical gears, bevel gears, worm gears, and planetary gears. Spur gears. This is the iconic gear. Simple and basic. They use straight teeth to transfer power within the same plane. They are cheap and reliable, but they suffer from backlash and noise. So if you want to know what backlash is, if you get two gears together and you mesh them together, you can wiggle them and move them slightly without them actually touching the teeth, within the air between the teeth. That's what we call backlash. It's pretty much undesirable in most cases, but sometimes it's fine to have a little bit of it in your mechanism. And in that case, you want to use spur gears. So what do I mean by say the same plane? Basically, they're just flat up next to each other. So you can't change the angle of the axle. Helical gears. The fancy slanted gears. The angled teeth guarantee constant contact between the teeth. So in this case, these gears have less backlash. They're also more efficient and quiet. However, these are more expensive and can cause unbalanced forces in the perpendicular direction. So what I mean by that, the angled teeth actually causes some crazy normal forces going on in the actual gears, which causes it to kind of shift along the axle when you have it. So you have to either use thrust bearings, which keep it in place, or have certain helical gears where you basically layer them up, but they're at the opposite angles from each other. So they all balance in the middle. Bevel gears. These are similar to spur or helical gears, but they are cones instead of discs. The purpose of these is to change the direction of the output shaft. In this example, the two intersecting shafts are perpendicular to each other. So, if you ever hear the name miter gears, they are just two equivalent bevel gears, so they have the same number of teeth, and they're 90 degrees. So, what I mean by cone is just like it's at a slant. You cut off the head of the cone. So in this case, you have both a gear ratio, you reverse the direction of motion, and you have that angle of the two axles. That's the point of bevel gears. Worm gears. These weird gears use a screw-shaped shaft to interact with a special receiving disc. This way, when the shaft is spun, the output gear will spin. So what's special about worm gears is that they are not back drivable. So not being back drivable essentially means that the screw can turn the disc, but the disc cannot in turn the screw. So if let's say you want a locking mechanism, so a motor that can't go backwards but only go forward, you would want to use a worm gear setup. In FRC, these are commonly used in snowblower motors. Now, the fanciest one is planetary gears. So these gears have a large inner gear called the sun gear and multiple smaller gears called planetary gears, which are wedged inside of a hollow disc with inside teeth. The purpose of these are to have very large and compact gear ratios, and these are very common for pre-made gearboxes. So when you look at this one to the right, we have a sun gear in the middle and a bunch of smaller teethed planetary gears. Now the gear ratio between the sun gear and the planetary gears is the actual ratio between. But if you just have one really large gear and a couple of really small gears, it'll be kind of weak. So what you want to do is have 3 smaller gears, and then you can layer them vertically so you can stack them and make really small, really, really large gear ratios. So I got a question in chat. Is the sun gear the one in the center? Yes. But wait, there's more. Idler gears. Besides transferring power and changing the ratio between torque and speed, gears also reverse the direction of rotation. If this is undesirable, you can use an odd number of gears to keep the same direction. These gears are called idler gears. So we have an input gear, otherwise known as a driving gear, and an output gear, otherwise known as a driven gear. So any gear in the middle would be called an idler gear. The main purpose of them, in this case, is to reverse the direction again and make it the same direction as the original. They also have another purpose, which is making gear ratios less extreme. In this case, the gear ratios would just multiply for the final result. For example, the idler gear on the right is both changing the rotation and making each individual gear ratio less extreme. So you have that nice gear in the middle just to make sure that the big gear does not have to directly contact really tiny gear. Makes things more reliable. So here's the anatomy of a gear. There are many important variables to consider when looking at a gear, but for now we will focus on the main ones: pitch, pressure angle, and pitch diameter. Note, these will all be listed by the manufacturer. So if you're buying a gear, which for most cases I heavily recommend, these will be on the website or on, they'll be listed by the manufacturer of said gear. So what's pitch? Pitch is the size of the gear teeth and is typically measured in inches. The important part to know about pitch is that gears need the same pitch in order to mesh. So I could go into the complicated geometry of what pitch is measured, but I decided that since manufacturers show them in the first place, it's better just to say that they're the size of the gear teeth. What's pressure angle? How steep of an angle between the tooth of a gear and the cylinder is attached to. Similar to pitch, gears require a matching pressure angle. So I want to really get this down. The importance of pitch and pressure angle is that if two gears don't have the same pitch and pressure angle, they will not work together. They won't mesh, they won't work. Make sure all gears you're using inside of one gearbox setup has the same pitch and pressure angle. Pitch diameter. It is a diameter of a circle in which two gears contact. So on this right, you can see the two pitch diameters, which is that red circle and the dotted black circle on the right. The place where the two gears contact in the middle, that is the place where the pitch diameters end. You can take the sum of the radii, which is the diameter divided by 2, of each gear, and now give us the center-to-center distances. Assuming a constant pitch and pressure angle, pitch diameter is solely determined by the number of teeth. So if you have the size of the teeth plus the angle the teeth has, then if you just change the diameter, then you'll have to change the number of teeth. And if you change the number of teeth, it'll have to change the diameter. One quick tip is if you want to actually get another way of, if you want another way of finding a gear ratio, just divide the diameters because it'll be the same as dividing the teeth. Any questions? So I was asked by chat, do idler gears have any impact on speed and torque? So if the idler gear is the same gear ratio, if it's a 1-to-1 gear ratio with another gear in the setup, if it's just made to reverse the direction, then no, it will not have any impact on speed and torque. However, if you do have an idler gear and there is a gear ratio going on in the idler gear, so let's say the first input gear to an idler gear is 3-to-1, and then the idler gear to the output gear is also 3-to-1, then the output gear would be 9-to-1. However, if you took the really tiny, output gear and just put it next to the input gear, it would still be 9-to-1 because the output gear will still be 1/9 of the size of the input gear. So it really depends how you make the setup, but I would say most of the time, the purpose of an idler gear isn't to necessarily change the gear ratio, but it is to make gear ratios less extreme. Someone else in chat, I've seen gears with just one much longer tooth. What would those be used for? I honestly I don't actually know what that you're talking about there. I'm probably going to look into it later and get back to you about that one. Yeah, I've yet to see one of those in FRC. The ones I got over are the ones I've actually seen in FRC. There's other ones, but they're really rare and you don't see them very much. Any more questions? Does someone ask, is there an upper limit? The upper limit you have is space, because the more idler gears you have, the more space it takes up. It's a fundamental flaw of gearboxes. So if you want to have more idler gears, it's fine as long as you have the space for it. Okay, let's move on. Chains and belts. Chain. What is chain? Chain is a series of metal links that can hold tension and interact with sprockets. Chain is used similarly to gears by transferring power between two axles. They also come in a variety of sizes, in this case called pitch as well. In robotics, the most commonly used is number 25, which we use for lightweight purposes, Number 35, which we use for, heavyweight purposes. And number 40, we barely use this, which we call bike chain because it's used on bikes. And this is super heavy duty chain. The only time I can ever think of us using this is if we have a lift that needs to carry the entire robot. Other than that, number 40 chain is just super heavy, waste of weight. Sprockets. Sprockets are toothed cylinders similar to gears, but they are made to mesh with chain. Also, like gears, different size sprockets can create gear ratios. However, unlike gears, they don't reverse the direction. So if you have two sprockets connected with chain, one sprocket rotating is going to cause the other sprocket to rotate at the same direction. Also, the chain needs to be kept in tension or to keep it from skipping. So skipping is when the chain temporarily falls off the sprocket and it starts missing. You do not want that. It's like having gears that only slightly touch each other but are not completely meshed together. It causes many problems, it wastes energy, and also might cause the gear to even fall off. So how do you keep tension? There are multiple ways to ensure good tension in a chain. Calculate the proper center-to-center distances, idler sprockets, half links, and chain tensioners. These are listed in order of most desirable to least desirable. So first we have center-to-center calculations. This is the first and most important step to properly tensioning a chain. We can use a chain calculator in order to make this easy. So the one on the right is the one I've used last season, which is called Recalc. So you have to input the chain's pitch and sprocket sizes and change the number of links until it's closest to desired center-to-center distance. I'm sorry, it's cut off on this slide. But essentially, you go here, you have the desired center-to-center, and you have the teeth of one sprocket, teeth of another sprocket, and then you'll tell you the amount of links. You can also change the links and try to get the center-to-center distance. One thing to note is that not every center-to-center distance can work with a combination of chain pitch and sprocket sizes. So you're going to have to typically choose the closest number to your desired length. Once you have the best compromise between links and center-to-center distance, add the following distances to the center-to-center for the design. So what I mean by this is you take the number the calculator gives you and add this. So for number 25, you add 0.018 inches. And for number 35 chain, you add 0.012 inches. So I stole this from a guide from NASA for FRC, and they stole it from the president of AvengerRobotics, and they claim that it can make more efficient power transfer if you add these distances by making it slightly more tense than it normally would be. And I'm not here to question the experts, so I would add these small little distances. Idler sprockets. Similar to idler gears, idler sprockets are in the middle of the input and output sprockets. However, these don't change the ratio as long as there is no load. So what do I mean by no load? It just means they're free spinning. If there's like any weight on them, it can change things. But if they're just free spinning, it won't change a thing. The purpose of these are mainly to tighten loose chain hanging due to gravity. These are very commonly used and have few trade-offs besides space. So honestly, I say for most mechanisms, unless the sprocket sizes are similar in a way that causes very little loose chain, I actually recommend having an idler sprocket just to make sure everything is tight. So in this case on the right, we actually have an adjustable one, which allows them to make it looser to take the chain off. As you can see by that sliding thing behind the idler sprocket. So we also have half links, which sometimes are called master links. These are smaller links that can be attached with another link without a chain breaker. So a chain breaker is just a tool we use to connect chain. These are useful when the center-to-center distance has to be between two links. So if you have a center-to-center distance that you need to have, and having one link makes it slightly less than what your desire is, and another link makes it slightly more than the desired length, and you have to have that center-to-center distance, that's where you should use half links. However, these are weaker than regular links and therefore should be avoided unless necessary. And now we have chain tensioners. These are inserted between links and can change their size with two nuts. So we'll just tighten or loosen these two nuts, and I'll change the tension. The main problem with these is that they can't roll over a sprocket. So if these go over a sprocket, it would break the chain. It just doesn't work. They have to not ever go over a sprocket. And therefore, motorized chains should not use these. And when I mean not, I mean almost never. Because if you motorize a chain, it will always have the entire ring of chain go over motorized. We'll go over these later, but the main purpose of chain tensioners is for virtual 4 bars. We also have chain inside tube. This is an advanced technique with chain, is to put it inside of 2x1 tube. This ensures that it stays tight, saves space, and looks cool. However, unless the design is tried and tested, which means someone else than you made it most likely, this should be avoided as they are extremely difficult to build and fix, especially at competition. So on this right, you can see an example of it. These are very commonly used in old style drivetrains before swerve drive became a thing. Any questions? Someone asked, will we be going over the different types of lifts? Yes, we'll go over different types of lifts later. Okay, let's move on. Timing belt. What are timing belts? Timing belts, specifically HTD timing belts, are used similarly to chain. They transfer power through tooth pulleys, similar to sprockets, and they typically don't reverse directions. However, unlike belt, the size can't be changed. So a chain, however, unlike chain, the size cannot be changed. So with chain, you can take off chain, add chain. With belt, you have a preset size. Benefits of timing belts. They're quiet, they're efficient, they're good for object manipulation. I put a star there because there's another type of belt we sometimes use for object manipulation, but it's still a lot better than chain, which has a tendency of shredding things apart. It also keeps bad habits from forming. For example, using half lengths. Since you have a preset size, you can't really make the timing belt weaker by doing things to keep it tense. Instead, you have to use the more good ways of keeping things tense. We can also make more complex paths. We can loop belts around things in a way that just chain does not work with. Here's some cons of using timing belts. It's harder to gain correct tension, only center-to-center distances and idlers. There's also limited sizes, so there isn't a size belt for everything. You also can't hold as much tension before stretching. Essentially, like outside of some cases, you shouldn't be using belts for very heavy lifts because they can stretch more easily than chain can. They're also harder to replace during competition because you have to have a very specific size. With chain, if you need to go to some other team to find chain, almost every team has chain you can borrow. However, with these specifically, you cannot. So the number one rule of belts is to always use a calculator and accurately determine pulley center-to-center distances. The only means of changing these once manufactured is adding idlers or 3D printing belts from TPU, and this is very not recommended unless it is complete necessary. I'd only recommend 3D printing belts if your competition is next day, you don't have the size, no one else is going to have the size, and you need to get it done now. Otherwise, they're weaker, they don't have as much grip, they stretch more easily, it's just not worth it. So now we have polyurethane belts, sometimes called polycord. These are elastic cords that can be used to transfer power as well. These can be customized relatively easily by melting the ends together. However, due to the lack of teeth in their pulleys, there is major energy loss when using these. So these are recommended mainly for conveying objects. So in FRC, sometimes you might see intakes or conveyors or indexes, it's very common for them to use polyurethane belts. They have a lot of friction. They grip onto the objects better than the flat side of HTD belts do. And unlike chain, they don't shred things. Any questions? Okay, great. Bearings and linear slides. Bearings. Bearings are components designed to restrict motion and to reduce friction. There are different types of bearings. There's bushings, ball or rolling element bearings, linear bearings, and linear guides. What is a bushing? This is the simplest and cheapest form of a bearing. They are simply holes made to restrict motion to be rotational. They are typically made up of materials with very little friction and are sometimes lubricated with grease. So we might use plastic or certain metals with low friction and rarely in FRC, but more so in professional world, you might use grease to lubricate these. These are really good when the load is too high for ball bearings and the speed is relatively low, so you don't have to have absolutely zero friction. Ball rolling element bearings. These are the quintessential bearings. Similar to bushings, they restrict rotational motion. However, they take advantage of the physical properties of rolling objects, balls, discs, etc., in order to further reduce friction. These are fast, smooth, and require little lubrication, but they do have lower load limits, especially at certain vectors. So for example, you don't want to have angled forces going on a bearing, or you might not want to press it directly into that center diameter area of the bearing. It's going to break it. So ball bearings in FRC. One of the best uses for ball bearings in FRC is actually using them to create turrets. The turret on the right uses the rolling element property of each ball bearing to create a larger bearing that can rotate with the motor. So essentially, like I said earlier, ball bearings use rolling elements, but we use ball bearings as a further rolling element in this turret, and it creates an even bigger bearing-like turret. However, always remember that there is a limit to the load on these bearings. Try to keep everything light and balanced. Essentially, you want the center of mass above the turret to always be above the center of the turret, if possible. Linear bearings. These are bearings designed to restrict linear motion, so up and down of shaft. They can be similar to either bushings, low friction materials, or ball bearings. Use rolling elements. The one to the right uses steel balls in order to reduce friction, so that one's more closer to a ball bearing. These are really useful for lifts in FRC. So linear guides. These are a type of linear bearing that wrap around or insert itself into a track. These can be made to work well with aluminum extrusion and rectangular tubing instead of circular tubing, which the regular linear bearing will work better for. These can also be made by using ball bearings. Example will be shown in the next slide. So here's some linear guides in FRC. This type of linear guide uses ball bearings in order to wrap around both sides of a 2x1 tubing. In FRC, this is commonly used for elevator kits, otherwise known as lifts. This shows how we can turn rotational bearings to linear bearings as well. So what are some uses for bearings? Bearings are essential in controlling motion. They allow for smooth operation of the machine without wasted energy and movement. They are also useful for allowing things to spin on a shaft without rotating the shaft itself. For example, we can use these to make free spinning pulleys. Bearing tips. Bearings can be both relatively expensive and time-consuming to insert into parts, and therefore we should limit their excessive use. For example, on an arm joint, only one section of the arm needs bearings on each joint. The other section can be directly connected to the axle. Essentially, if it works with just one set of bearings, don't use two. Also, bearings don't take rotational force as well, so make sure that any axles supported by them are not cantilevered, which means supported only on one point. The center of mass on the axle should typically be centered between the two bearings. Sometimes it's impossible to do so, and if it is, at least try to use two bearings on one hand with a small amount of separation. The bigger the separation between the two bearings, the more reliable the bearings will be. Any questions? So someone in chat said, if you're in such a dire need for a belt, would it be better to just use chain? So I'm assuming they're talking about 3D printing TPU belts. I would say yes. If it is possible to use chain instead of belt in that case, I would more so recommend to use chain or polyurethane cord than it would be to use TPU belt. However, in the case in which it is the only possible solution, you can 3D print belts. It's something you can do. I don't like it very much. Any more questions? I feel like it's not smart to have only one way to do it, right? Yeah, I agree that if you're designing things, designing it in ways in which you can replace is a smart thing to do. However, I'll go over this more in the design strategies lecture. I just wanted you guys to know that 3D printing belts is a thing you can do. Okay, let's move on. Linear slides, the fun part. What is a linear slide? Linear slides are mechanisms that take advantage of linear bearings and pulleys, or rack and pinion gears, to extend or retract a part of the machine. These are extremely useful in FRC, as typically games require you to expand your robot past the initial size limits. Types of linear slides. The three main types are lifts/elevators, slide rails, and telescoping lifts. Lifts or elevators are used for high weight applications, for example, lifting the robot, or another example, moving a second arm up and down. Slide rails are used for fast and smaller applications, so moving an intake. Telescoping slides can be used for either. Lifts or elevators use linear guides and aluminum extrusion/tubing in order to move a central carriage. These are larger, but are capable of handling high weights. These mostly use either chain or belts in order to move. When you rotate them with a sprocket/pulley, the part of the chain belt that stages are attached to will move up. Essentially, the distance between the initial rotating point and the point in which the chain is connected to the stage gets shorter as you rotate it. Therefore, it would have to move up. Slide rails. These are similar to drawer slides, where one section will be inserted inside of a rail section and they use string to pull instead of chain/belts. These take advantage of metal balls, like ball bearings, in order to further reduce friction. These are fast and lightweight, but they can't carry much and are weak. Due to that reason, they are more popular in smaller robots like FDC. However, they can be used in FRC with certain applications. For example, if you're stacking two linear slides next to each other where you have one vertical and one horizontal, these are really good as the horizontal linear slides as they're more compact and they're smoother. Telescoping lifts. These are similar to regular lifts, but instead of having the stages built inside of a frame, they place the stages telescoped inside of each other, similar to the slide rails. These are good for when the lift needs to be very compact. However, these can be weaker than regular lifts and can also be limited due to in carriage size. These are good for climbers and light intake/scoring mechanisms. So one year these were extremely popular was in Rapid React, where there is this mechanism called a climber in a box that were used to climb up the bars. Any questions? All right. Linkages and springs. Linkages. What are linkages? Linkages are a series of geometrically linked parts that have joints between them. They are used to limit the range of motion in a more complex way than just bearings can alone. They take advantage of the properties of certain geometric shapes, such as triangles and parallelograms and ellipses. Types of basic linkages. There are thousands of different linkages, but the most widely used in robotics are the 2-bar linkage, the 4-bar linkage, cams, and scissor lifts. The 2-bar linkage. These utilize 2 bars that have free rotating joints and a sliding area with confined linear movement in order to make an imaginary triangle and use that geometry to move the sliding part back and forth. So in order to better explain what I mean, I made this yellow triangle. I made this yellow triangle in order to show the triangular shape that's going on here. So if you were to try to rotate the first bar forward, the first angle is going to decrease and it's going to increase the right angle. And that's going to push everything forward. So here we have a 4-bar linkage. These utilize 4 bars that together create a parallelogram. This parallelogram ensures that both sets of sides always stay parallel. This is very useful for arms that require the end to always be perpendicular to the ground. So here we have a case of an FTC robot. And here's the parallelogram. So as we can see that Y, the end of the arm, is always going to be parallel to the tower the arm is staged on. We also have virtual 4-bar linkages. We can use belt or chain in order to fake a 4-bar effect. I put fake in quotations because it's actually the same thing. This is because the chain itself creates the parallelogram geometry and rotates the sprocket to maintain it. This is useful if you need the mechanism to rotate past 120 degrees. So we look back at this slide, you can realize that this won't be able to go above the top of the arm. but this arm can actually go a full 360. And here we show the geometry that maintains the parallelogram. Cams. These use a pointed ellipse shape rotating around an axle in order to cause a repetitive linear movement. This has few uses in robotics, but if you need a repetitive and small movement, these work well. Scissor lifts. These are similar to linear slides in a sense that they can create rapid expansion. However, they're notoriously difficult to pull off, break easily, and should generally be avoided unless necessary. So they work similar to all the other linkages. They just use geometry. They change the angles in order to make things go up further and less far. So here on the right, we can see the geometry behind a scissor lift. But like I said, really difficult to pull off, rarely ever better than any other solution for the same problem. I don't recommend using them much. They're essentially the 3D printed belts of linkages. Any questions? Someone asked pros and cons of a 4-bar versus virtual 4-bar. The pro of a regular 4-bar is that they're simpler, less likely to break because you don't have to deal with the chains and the sprockets. And the tension in a chain can sometimes cause some unbalanced forces occurring within the arm itself. And like I said earlier, the pros of the virtual 4-bar is that I can go full 360 degrees without breaking. Overall, I'd say is that in FRC, just due to the sheer size of the arms, a virtual 4-bar is better, and that's because they're typically also more compact. Regular 4-bars are larger, they take up more space, while virtual 4-bars are really compact and simple. And if you use that chain and tube mention I mentioned earlier, it can be inside of the arm itself, though that's a bit more complicated. Any more questions?
What's stopping the end of a virtual 4-bar from just like flopping around? Is there like a chain tension?
Okay, so the way it works is that the top sprocket on the arm itself is going to be still. It's not going to rotate, and only the end sprocket will. So there's going to be tension in the chain that'll keep the second part of it flopping around. So only one of the sprockets will free rotate.
Oh, thank you. I thought both sprockets were free spinning.
Yeah, I just now realized I probably should have emphasized that. But yes, only one of the sprockets free rotate in a virtual 4-bar.
Thank you.
Any more questions? Springs. Why do we use springs? Springs, like batteries and air tanks, are energy storage devices. The more compressed or stretched they are, the more energy they hold, and therefore the more force they output. In FRC, we use springs mainly to balance forces in the robot, especially counterbalancing gravity. There are 3 types of springs commonly employed in FRC: compression springs, extension springs, and constant force springs. Compression springs output more force as the spring is compressed. The most common example of these in FRC are gas springs, which are similar to pneumatic cylinders, but you can't change the amount of gas in them. So as you compress the gas spring, the gas gains more pressure and therefore outputs more force. These are almost always used to counterbalance arms against the force of gravity. So on the right, we see a robot from the very famous team Cheesy Poofs for the 2019 game, Deep Space. And on this robot, they actually used gas springs in order to maintain a counterbalance force against gravity. Extension springs. Extension springs are springs that output more force when stretched. The most common form of these in FRC is polycord. These are mostly used to counterbalance arms and to keep mechanisms from falling too far. So on the right, we have a very notorious team called 7451 AvengerRobotics, and they employed a piece of polycord in order to be a extension spring on their robot in order to counterbalance their arm against gravity. In this case, it worked really well. It did exactly what they wanted to do, and it had no problems with it whatsoever. And here we have constant force spring. Constant force springs always coil up and output the same force. These are oftentimes used in FRC to change the balance forces in a mechanism to be at rest at a different angle. These are often shaped as strips of metal coiled up. So a really good example of this was Walton Robotics 2022-2023 FRC robot. Yeah, 2023 FRC robot. And for them, and charged up. And they actually were able to change the angle of their lift by using a constant force spring and a pulley. Any questions? Someone asked, do gas springs use gas like petroleum? I didn't know that was allowed. No, gas springs, like they do use gas, but they don't use petroleum like gasoline. They use gas as in the state of matter, like the air you breathe is gas or nitrogen is gas. That's funny though. Yeah, if they used gasoline, they would not be legal. All right. Actuators. What is an actuator? Actuators are mechanisms that convert energy into mechanical force. These are necessary for robots to, quote, create movement. The two types of actuators in FRC are electric motors and pneumatic cylinders. Motors. Electric motors use electromagnets in order to turn electricity into rotational motion. There are 5 commonly used motors in FRC: a Falcon 500, Neo, Sim, Neo 550, and Redline. Falcon 500s. These are the most powerful and most expensive motors in FRC. However, due to their power, they are often overkill for many mechanisms. You should mainly use these for drive chains in high speed and high torque applications. So these are what you use if they're the only thing you can use. They're extraordinarily expensive, and more importantly, they take forever to get because they're always out of stock. So most teams outside of the very best have very limited supply of these, and are almost always used for the drivetrain. Essentially, unless you have to, don't design your mechanisms for Falcon 500s. If they can only be done with a Falcon 500, probably should try to change the mechanism. Neo. This is a similar motor to the Falcon 500, but it is easier to get, but less powerful. These are the motor of choice when the application doesn't need the full force of the Falcon, but requires being lightweight and power nonetheless. Essentially, these are the slightly worse version of a Falcon 500, but since they're slightly worse, they're a lot easier to get. Sim, the grandfather of FRC motors. If you look back just 15 years ago, every single robot were full of these things. They're big, heavy, and less powerful than their newer counterparts, but they're also extremely cheap and reliable. They're essentially like the 1996 Toyota Corolla of motors. These are dying out though. But if you have a mechanism that doesn't need a lightweight motor and you're running out of Falcons and Neos, use these. Some teams have been starting to use them and they have been successful. They're still good motors, just old and very heavy. Neo 550s. This is the lightest FRC motor. These are used for applications where being lightweight and speedy are important. So for example, intakes, small linkages, etc. These are also really small and can fit in tighter spaces if needed. I don't fully recommend this. I always try to design things so it's easy to access. However, if you do need to put a tight motor in a very tight space, this is your only motor you're going to do it with. Love these things. And now finally we have the Redline. This is the older brother of the Neo 550. It's generally lighter than a Neo or Falcon, and it's useful for more high-speed applications. They're also cheaper and more reliable than Neo 550s. These are basically the Sim of Neo 550s. They do the same purpose, but they're easier to work with and they're bigger. Pneumatic cylinders. Instead of electricity, these use air in order to generate movement. Unlike motors, these create linear movement. The main purpose of these are to have fast and light ways to move heavy mechanisms. Their main drawback is that the amount of air is limited. Therefore, if you use these too many times during a match, you'll run out. Some good mechanisms to place these on are claws, moving intakes, and arms to 2 rotation points. So essentially, if you have a set up position and a set down position, these are really good. Types of cylinders. The 2 types of pneumatic cylinders are single acting and double acting. Single acting has 1 port and uses springs to decompress. Double acting has 2 ports and need opposite airflow to decompress without help from other forces. In FRC, we mainly use double acting cylinders, but there are some cases where single acting cylinders might be preferable. mainly places where you don't want to use a lot of air. Pneumatic math. If you want to find the max force of the pneumatic cylinder in FRC, multiply the bore radius squared, and the bore radius is just the bore diameter divided by 2, with pi times 60 psi, the max working pressure. Also remember that the stroke is the outer length once extended, not the total length. One thing I forgot to put here is that if you're trying to do the retraction force, take the force you calculated earlier and subtract the force if you use the rod diameter instead of the bore diameter. There you go. Any questions? Okay, guys. My final thoughts. This has been a really fun one to make, but there's also a lot of content, which you can see by the sheer amount of errors I had in here. Sorry for that. Less so than physics, I don't have as many final thoughts to say. I think overall, it's pretty self-explanatory how this is useful for robotics. I really want people to get home that these are all mechanisms that they do have access to. I think hopefully everyone learned at least one new type of mechanism they haven't seen before, especially those who are newer to robotics. And that's about it for today. I hope everyone has a good week. See you guys later.